Hello students, I am Dr. Arvind Kumar from Department of Physics, D.A.V PG College C1. Today we shall discuss interference of light. What do you mean by interference of waves? As we know in the previous classes, in the phenomena of interference, two waves of similar nature superimpose each other and redistribute energy. Interference is just the combination of waves. Interference of light waves can be described in terms of electric field. In the interference, the two waves think of two simple harmonic waves with same angular frequency omega and equal amplitude A, as they both pass through the same point in space. The two waves may, however, have different phasage. These waves can be described by the following equation. E1 is equal to A sine omega t and E2 is A sine omega t plus phi, where phi is the phase difference between the waves and omega the angular frequency of both the waves. Here the total field is found by using the principle of superposition, which says that the total field is equal to the vector sum of the individual wave fields. After combining these two equations, we get E is equal to E1 plus E2 is equal to 2A cos phi by 2 into sine omega t phi by 2. And this equation can be rewritten as E is equal to A1 sine omega t phi by plus phi by 2. Here AT is used in place of cos phi by 2. That means AT is equal to 2A cos phi by 2. Because amplitude of each equation is where the new total amplitude is AT is equal to 2A cos phi by 2. Here the graphical representation of the interference, the leftmost figure, two waves are shown in same phase. That means phase difference between them is 0. The resultant wave has greater amplitude. In the middle figure, these two waves meet in the phase difference of pi by 2. So the resultant amplitude, resultant electric field has a smaller amplitude, and in the last rightmost graph, the two waves are shown to meet in opposite phase. That means phase difference of phi, and therefore the resultant intensity becomes 0. Important things to note about this example are that the amplitude of the total electric field depends upon the phase difference phi, and the angular frequency of the resultant wave is still omega. Two special cases are of interest. If the waves are in phase, that means phase difference phi is equal to 0. So the resultant amplitude is twice the amplitude of one of the waves. We know the intensity of a wave is proportional to the square of its amplitude. Therefore, the intensity of the resultant wave is 4 times the intensity of one of the original waves. Here, the terms constructive and destructive are sometimes used to describe these interference maxima and minima. As we know from previous classes, constructive interference takes place at those points where the two waves meet in phase. That means same phase. And destructive interference happens at those points where the waves meet in opposite phase. Young's double experiment. This is the first experiment which shown the phenomena of interference of waves in laboratory. That means interference of light. This experiment is popularly known as Thomas Young's double slit experiment. In this arrangement, there is a source of light, a colored filter, an opaque plate with a narrow slit cut into it, another plate with two narrow slits in it, and a white screen for viewing the light. Each of the slit is quite narrow, typically less than a tenth of millimeter, and the two slits in the second plate are usually separated by only a fraction of millimeter. Light travels from the source through the filter to the first slit, from where it travels to the plate with slits where much of it is blocked off, but some can get through both the slits. Some of light which finally gets through is intercepted by the screen. This is the elaborated figure. We can imagine when only one of the slit in the second plate is open, there is a diffuse pool of light on the screen. This patch of light is wider than the slit that the light came through. This spreading out is called diffraction, a topic which will be taken in the chapter of diffraction. When light passes through each of the pair of slits in turn, keeping the other slit covered, you can see a pool of light on the screen. The areas covered by these two pools of light overlap considerably. So one would expect naively that with two slits open, the resulting pool of light would just be a merging of two pools already seen, bright in the middle and falling off at the edges. These expectations turns out to be quite wrong. Instead of a continuous patch of light, there is a pattern of light and dark strips called interference fringes or pattern. The ray model of light has no hope of accounting for that. This is the twin slit interference pattern. This contains bright and dark fringes. At some places where there used to be light from each slit separately, there is now darkness. But the energy in the light has not been destroyed. The brightest part of the fringe pattern are now more than twice as bright as the brightest part of the light pool from one slit. The energy of the light has just been redistributed. Although Young's original experiment used white light, the contrast between light and dark fringes is enhanced if a suitable colored filter is used to restrict the range of frequencies in the light. The fringes are sharpest when a very narrow range of frequencies, monochromatic light, is used. The explanation of Young's experiment needs the wave model of light. To see how the wave model works, it is useful to study a similar experiment using water waves instead of light, in which the superposition of waves can be seen directly. Here a pictorial representation. The explanation of this as many aspects of wave behavior can be observed in water waves. In a simple direct analog of Young's experiment, a straight line water waves, analogous to plane waves in 3 dimensions, are generated by a long pedal. The waves travel to barrier with 2 narrow slots in it. When only one slot is open, diffraction can be observed. The waves are spread out instead of forming a sharp shadow. Each of the wavefront coming out of the other side has a roughly circular shape, but the amplitude of the wave is weaker at this side than it is in the straight through direction. When both slots are open, A new feature called interference is seen. There are some places where there is practically no wave disturbance and others where it is quite strong. In the case of water waves, the wave's disturbance can be taken to be the displacement of the surface of the water from its equilibrium level. The amplitude of the resultant wave pattern varies from minimum of 0 to some places to a local maximum at other places. Furthermore, although the wave disturbance at any place varies in time, the amplitude at any single place is fixed. At a place where the amplitude is maximum, say A, the wave disturbance varies from a minimum of minus A to a maximum of plus A. At a point where the amplitude is equal to 0, there is no net wave disturbance at any time. The amplitude of the resultant wave changes continuously from point to point between the locations of the maxima and minima. Here the pictorial representation of interference of waves. Here the dotted line shows the trough of the waves and full line shows the crest of the waves. In this example, the location of the points of maximum and minimum amplitude all lie on approximately a straight lines radiating from a point midway between the slots. If we look at the resultant wave at places in between the position of the maxima and minima, we can see that the amplitude varies smoothly with position. So it's how the intensity varies with position on the screen for a typical Young slit experiment. Now we can say the interference is the principle of superposition, which says simply that the combined effect of several waves at any place at a particular instant of time is given by the sum, generally vector sum, of the wave property of the individual waves. The contribution from one wave is just that which would occur if the other waves were not there. In the case of water waves, the appropriate wave property is the linear displacement of the surface of water from its equilibrium position. In the case of light waves, the appropriate wave property is electric field, which is directed, in the direction which often point in any direction perpendicular to the direction of propagation. The interference pattern can be understood in terms of superposition. There are some places where the crest of one water arrives at exactly the same time as the trough of this wave from the other slot. At any one of those points, the net displacement for these two waves is a minimum 0 if the amplitudes are equal. Although the crest of wave 1 and trough of the wave 2 move on, the sum of the two wave disturbance at the same fixed point in a space remains 0. There are other points where crest always arrives in a step with a crest and trough with a trough. At those points where crest or trough and trough meet, amplitude of the resultant wave turns out to be sum of the individual amplitudes. There are many places where the individual waves add to give other values of the resultant amplitude. In Young's experiment with light, the function of the single slit is to ensure that the light falling on each of the pair of the slit is coherent. Although light consists of a continuous distribution of component waves with different frequencies and wavelengths, light reaching each of the twin slits from the narrow single slit has the same composition. If the pair of slits is placed symmetrically, then any change in any component of light, including any change in phase, occurs simultaneously at both slits, so the slits behave as a coherent source. It is easy to calculate the points in a space where maxima and minima in the interference pattern occur. The analysis is essentially the same for the water waves example and for the Young's twin slits because both can be treated in two dimensions. The wave amplitude at some point P depends on the phase difference between the two interfering waves. If the waves are in phase, at their sources, then the phase difference P is determined by the difference in time taken for the light to get from the source to P. That time difference in turn depends on the speed of the waves and the difference in distances called the path difference traveled by the two waves. In the case of light, we can say that the phase difference is proportional to the optical path difference, which is the product of the actual path difference and the refractive index of the medium. That means optical path length is equal to n times geometrical path length, where n is the refractive index. We usually consider Young's experiment in here. The optical and geometrical path difference are essentially equal. The path difference for Young's slit is level D. This analysis is valid only if the screen is a long way from the slit and if the point P is close to the central axis. If those conditions are satisfied, rays from each of the slit P are almost parallel, and it is said that experiment satisfies Fraunhofer diffraction. If the optical path difference T is equal to the whole number of wavelengths, then the phase difference will be n times 2 pi, and the two waves will be exactly in phase. Therefore, the condition for a maximum is D must be equal to m into lambda, where lambda is the wavelength and m is equal to 0 plus minus 1. That means any integer. The value of m is called the order of the bright fringe. The fringe in the middle is the zero order fringe. A minimum in the amplitude will occur if the optical path difference is equal to an odd number of half wavelengths. That means for a minimum, the path difference D must be equal to m plus 1 by 2 into lambda, where m is again either 0 or a positive or negative integer. Since the intensity in the interference pattern is proportional to the square of the wave amplitude, maxima and minima in the intensity occur at the same places as the maxima and minima in the wave amplitude. The relation between phase difference phi and path difference D, which applies at all points including those between the intensity of maxima and minima, is phi by 2 pi is equal to D by lambda. These results apply to all kinds of interference between two elementary waves. Here the pictorial representation to location for maxima and minima. The location of the points in the interference pattern is most conveniently specified in terms of the angular position theta of the point P. The angular position P is measured from the midline between the slits. It can be seen from the diagram that D is approximately equal to D sin theta. So the condition become for a maximum m lambda is approximately equal to D sin theta, and for a minimum m plus 1 by 2 lambda D sin theta. This formula gives the angular position of the bright and dark fringe in the space. It follows from these equations that the fringe spacing, the distance between two consecutive light fringes or two consecutive dark lines on the screen, is given by delta y is equal to lambda x upon D, where D is the distance between the slits. These results illustrate why we can see good fringes pattern only if the range of wavelength in the light is small. If the fringes are observed on a screen a long way from the slits, the intensity of the fringe is fairly uniform. The missing intensity from dark fringes has gone into the extra intensity of the bright fringe, so that there is no violation of energy conservation. On a distant screen, the fringes are uniformly spaced and the separation is approximately equal to lambda x upon D. Here is the pictorial representation of the idealized intensity pattern for Young's twin slits. The important points to be noted is that for a fixed wavelength, the fringe spacing varies inversely with the separation of the slits. If the slits are moved further apart, then the fringes get closer together. For a fixed separation of the slits, the fringe spacing is proportional to the wavelength. There is always a bright fringe on the central axis. So when light is used, the only bright fringe which shows up strongly is the central one, because its location does not depend on the wavelength. Since the fringe spacing depends on wavelength, the total pattern for white light is a continuous mesh of overlapping fringe pattern. The overall effect is white light in the middle and washed out colored fringes on the sides. Yes. Thank you.